working inside chapter 9, which deals with logic family characteristics, and y'all have to help me to remember where we were at. We went over the basic makeup of a standard TTL gate. So this would be a 2-input NAND gate. We talked about the input current high, input current low, current output high, current output low, syncing and sourcing. Are you okay on those terms? Okay. Then we talked about the input current low and the input current high. We were looking at what we refer to as fan out. So what is fan out? And you won't find it in the data sheet, but it's a term that we use quite often. Nobody knows. Anybody can take a guess. Fan out. Nobody's going to take a guess. So what we're doing is we're talking about the output of a gate. So let's say this is a 2-input AND gate. Well, we know when this guy here outputs a high, we say it's sourcing. And we know the current flow is into the gate. But we have what we call, but this guy, let's come up here and say we're hooking this up to an input. And here we'll just use an inverter because it's easier just to draw one input like that. Okay. So this would be the input of the inverter. Okay. And this is going to come over here and feed into that. Okay. And then up here we have the resistor. So that's what they're doing. What they're doing there is drawing the input. This is the basic input of a NAND gate, but what they've got is they've got this input connected high all the time, so it's going to act like an inverter anyway, right? Understand that? So when we output a high, then this guy right here is going to take so much current to turn this transistor on, right? You understand that? And then this would be listed as IN high. Now, this current flow is going to come into this guy, okay? And if it's going to come into this guy, so let's source first, and it's going to come up. And this is not quite right. Let me redo this. In fact, let's do a low, because the low goes through here. We'd have to see the rest of the gates, what we'd have to do. So we're outputting a low out of this gate. So if I'm outputting a low out of this gate, then current flow is going to come up, right? You understand? It's going to come out of the gate. It's going to come over here. It's going to come up here. And it's going to take so much current to turn this transistor right here on. And this is what that IHN current is listed. Of course, here they're telling us 1.6 milliamps. Everybody understand? Now, this guy right here, according to this, it can only drive what? 16. So how many, if this input requires 1.6 milliamps, this guy can sync 16, how many inputs can it drive when it's outputting a low? 10. Well, we call that the fan out. So that means this guy here has a fan out of 10 because it can drive 10 other inputs of the same logic family. And if you look, I don't know if they show the other or not. So this is sourcing. So when we source, and they don't show the rest of the current flow when we source, but when we source, the current flow comes through here. We can't see the rest of the circuit. And then it comes up, and then it goes up through the source and transistor. Now, the problem here is we put that 130 ohm resistor in there to protect the gate, right? You understand? Because if I was to accidentally ground this or ground it on purpose, we can literally connect the output of a TTL gate to circuit common and not hurt the gate because of that 130 ohm resistor. But right off the bat, you know, we can't get 16 milliamps for a high, right? Down here, we don't have anything to go through. This is nothing but a transistor. So here, according to this input right here, when I'm going this way, requires what? It requires 40 microamps because we're turning it off, right? You understand that? So we need to get 40 microamps. If I'm outputting my worst case here, which would be 2.4 volts, they're saying this guy here needs 40 microamps. And we got to make this gate drive the gate in the worst case scenario, right? You understand? Everybody okay? So if this takes 40 microamps, and right now we have it hooked up to two inputs driving this high, then that's going to be, here they say 2 times 40 would be 80, right? 80 microamps. So what I need to know is how much current would this guy be able to source. And here they don't show us that, but we can look at it. This would be I out for a high. Everybody else okay? Now what you do, let's say it's 200 microamps. So we could put out an I out low, it could do 16 milliamps, but the I out high is only 200. So here we say we had a fan out of 10. This could drive 10 other gates, right? You understand? And this right here would have a fan out. This guy here could drive 5 gates. So what would be the fan out of this guy right here? What would we measure? What would we say it would be? Well, we'd say it would be 5. Even though it could drive 16 milliamps worth of sink current, it can only do 400 microamps of source current, and you rate it, like when we rate a chain is rated as its weakest links, right? Not its strongest link, its weakest link. So we'd say this guy has a fan out of 5. That makes sense? Are you okay? So what is fan out? The fan out is the number of light gates that it can drive. So a light gate would be like a 7400 driving a 7404. It would not be a 7400 driving a 74 LS04. Or it would not be a 74 LS04 driving a 74 LS100 driving a 7404. So we're talking about like families, right? You know, understand when we do the fan out, it's talking about like families. So standard drive out, fan out for a standard gate is 10, and we could look at the data sheets on that. 74 LS04s, we'd have to look at that and see what the fan out would be. No, it's the current drive capability. So what changes with these? What changes when we go to a different family? So I've got a 74. I got a 7400. I got a 74 L100, which we can't find anymore. I had a 74 H100. I had a 74 LS100. I have a 74. I have a 74 LS100. I have a 74 S100. I have a 74 HC 100. I have a 74 HCT 100. Now, what are those center letters telling you? Well, not only the speed, it's telling me the power. Okay, you understand? So if I use this and I feed this, then the fan out is no good anymore. So if I say it's got a fan out of 10, that means it's got the capability, it's got the power, it can maintain it to drive 10 inputs of the same family. So this is one reason why data sheets don't put fan outs anymore. They still teach it in books, but they don't put it in the data sheets, but they do put the current. So if I come over here and look at the data sheet of so y'all bring up Blackboard and let's look at some data sheets. And I think we have a 7400, and I think we got like a 74 LS04. We'll look and see. So these were the ratings that we were looking at. But well, like I say, you need to understand fan out because you're going to read about it. But data sheets don't give fan out because they don't know what you're going to be driving, right? Oh, wrong class. Yeah. I got solid state on my mind, guys. Though. So here's the 74 LS 100, and then we're looking for there's a pin out. That's what the National Semiconductor calls the function cables. That's what our book teaches as a truth table. And then I come over here, and this gives us our standard TTL. Standard TTL or TTL looks for a power supply of the 7400 series. Let's rephrase that. Wants a power supply of 5 volts plus or minus 5%. That's really common there too. But here it says, okay, VN high. So this guy right here is going to require 100 milliamps. I'm sorry, VN high right here. This guy is going to require 360 microamps. So make sure I'm on the right thing. VN high, I'm sorry, right here. 20 microamps. Sorry, let me blow this up. Let's see. Because I don't get off on. Yeah, we're looking for, I'm sorry, IN high. IN high. This is what we're talking about right here, right? Yeah, it's going to be 20 microamps. And then IN low is going to be 360 microamps. And that's how much this gate would require for a high or required for a low. Okay. This guy here can output. So here's our output right here. So it can output 400 microamps for a high, and it can output 8 milliamps for a low. So how many loads can it drive? Well, we come over here and we take the high output current, which is 20 microamps, right? IN high, excuse me. So IN high is 20 microamps. I out high is 400 microamps. So how many loads could it drive? How many of these could it drive? Looks like 20, right? Don't understand that. But then I come down here, my output load current is 8 milliamps. This guy says my output low is going to require 360 microamps. So how many loads can that drive? Well, I would take the 8 milliamps and I would divide it by that, and that would come up and give me the number of loads, right? Which would be a little over 16. Well, what we'd do is we'd rate it at its worst case. But if I come over here, so write these down. So how much can this guy here drive? 8 for a low, right? And 400 microamps for a high. I explained the minus. Why is it minus? Huh? Yeah, it's going into the gate. So high, the current flow is into the gate, right? Lows, the current flows out of the gate. So don't get that confused. It's not that the polarity change, but we're literally changing the direction of current using that sinking and sourcing transistor. So this is the LS. This is the 7400. And of course, when we go out here and look at those same settings, so this guy here for a low, we can drive 400 microamps, which is the same, right? You understand? But all of a sudden, this guy right here can drive 16 milliamps. So I mean, this guy could sure enough drive a lot of LSs, right? You understand that? But it can only drive 10 standard series. So this is why they don't give fan outs again, because fan outs determines what type of logic this gate is driving, right? You understand that? What family of logic is driving? Fan out is. Fan out is not assuming. Fan out is that is right. That is what you said. It doesn't assume. It means you have to stick with the same family. Yeah, but you're not going to run into that much anymore. Uh, Predominantly, it's going to be the same logic, but it all depends on what speed and what power you need. So S is still S is in TTL. By the way, the S series is the fastest guy we got, but it consumes more power. Uh, it's got a propagation delay of like 3 nanoseconds. Standard TTL is 10 nanoseconds. LS is around 10 nanoseconds. LS is around 9. Excuse me. Well, you could. So of course, what you're doing is shooting for price. If you're not shooting for speed, then you're shooting for price, right? So it's gonna depend on what you're doing, and the bigger the circuit is, and the more logic that the signals have to travel through, the more likelihood you're going to use higher speed chips. Because every time you go through one, it adds a delay. So this guy here has a propagation delay of, here's propagation delay right here, of 22. This guy here has a propagation delay of, it says 15 and 22, but if you go to a low, you got to go to a high, right? You understand? Yeah, so 22, if I was trying to time, I would use 22 nanoseconds for the output to respond to the input, and that's guaranteed. All right, understand? When I go back over here, and this was the standard series. In propagation delay, that's how long it takes for the signal to get through the gate itself. Okay, y'all understand that? So the book will talk about fan out. I'm not sure if this book does or not, but you will definitely get in or hear that term about the fan out, but you got to understand it's a relative term, right? Depending on what you drive. The input high and input low voltage levels, are you okay there? So for standard T, we're going to use, what do we use? If we don't know that, what are we going to use? So normally we have values that we use if we don't have data sheets. Okay, so the value we use for current is normally the 400 microamps and the 16 milliamps. Most of the time it'll get you by, but sometimes it won't. For voltage levels, we're looking for what for a high? What are we looking for a high? 2.4, above 2.4 or greater, and 400 millivolts or less, right? And that's generic. When we start looking at these data sheets, this will be fan out, guys. We're looking at V out low, V in low, V out high, and V in high. So notice standard is V out high, worst case. We need to get above 2.4, but that's worst case is 2.4, right? You understand? They say it's typically for TTL, it's around what? 3.6. Oh, I'm sorry, 3.4. And it says the maximum input is what? For a low is 400 millivolts, and this is out. In is what? 800 millivolts. So the output is guaranteed at 400. The input says I'll accept 800. So we've got a 400 millivolt safety margin built in there, right? You understand? The output is guaranteed at 2.4. The input says I'll accept what? 2. But is this going to be? This is what we use for rule of thumb. To actually get in and figure out exactly what it's going to be, then what would we do? We'd look it up on a data sheet. So this says right here for this one, This is the 7400, and of course these are true. So this is right off the data sheet. So this says this guy will output a minimum of what? Now look, this says if VCC is minimum and the output load is maximum. So that means if we're putting 4.75 volts on this thing, okay, y'all understand that? 4.75 volts, and we're pulling 16 milliamps, they still, or we're pulling 400 microamps, they still guarantee at least 2.4 volts. By the way, this is called the commercial. This is called the commercial series, the 7400. This is what we call the military series or mil specs. So this is a mil spec. This is standard. So 5400s, notice they have greater voltage margins. So a 5400 would have a voltage margin of a VCC percentage of 10%, where a 7400 the 7400 series is 5%. So this is what's called military grade. I'm sorry. But if I come over here and look at another gate, so let's look like at a LSO2. Which is a NOR gate, right? And then we come up here. Notice the range of voltages are still the same. But when I come up here and look at my high level output, this guy right here don't say 2.4. It guarantees what? 2.7. And then for my low level output, it don't say 400 millivolts. It says 350 millivolts. But still, the 2.4 and the 400 millivolts is good rule of thumb, right? You understand what I'm saying? Even though they do vary between gates. Are we okay? This guy here has a propagation delay of 15 to 18 nanoseconds. So this one is a little lower. This guy right here did away with the standard series. So after the LS series came out, the standard series started disappearing because it has a little bit of propagation delay and it consumes less current, but it can't drive quite as much. Are we okay? So that's VN high, VN low. Rise time, we talked about rise time. Rise time is usually not given on data sheets, but rise time is measured between where? 10 and 90% of the actual value. So rise time is the time it takes for it to go from a low to a high, right? And then fall time is the time it takes to go from a what? A high to a low. Are you okay? Now, what is important is this guy right here. This is propagation delay. So time propagation low to high, and this would be time propagation high to low. And what is propagation delay? Huh? Yeah, it's the time it takes to go through the gate. So what it is it's the time it takes when this goes high. Well, how long is it going to take for that to go low? It can't be at the same time, right? The output cannot respond, right? Just like you're out there in your car and you slam down on your gas pedal, you're not going to go from 0 to 60 in no time. It takes time for your car to do what? Respond to the command. Even in dragsters, they get up there pretty fast. I mean, even rockets, when they launch them off a launching pad, they don't get up to thousands of miles an hour in no time. It's still got to propagate through the system, right? So these are some examples. So what would happen? So this is an AND gate wire. What function does this AND gate right here do? What circuit? What does this do? It's not an inverter. Yeah, but what is it doing? Connected together, yeah. A short is an undesirable. So short in this way, short wouldn't be a legal term, even though we do it a lot, because a short is an undesirable path for current to flow. This is not an undesirable path. This was done on purpose. We call this a what? So this is serving the function of a buffer. Yeah, this right here serves this guy right here. It's not, or it's a NOR, right? This is an inverter or a NOT, and of course this right here is an inverter. That's a true inverter. Now, what you have to understand. So let's just generically, let's say this guy right here gives us a propagation delay of 10 nanoseconds, and this guy right here gives us a propagation delay of 10 nanoseconds, and this gives us a propagation delay of 10 nanoseconds. Then how long would it take this output over here to respond to this input over there? Yeah, it would take 30 nanoseconds. So we use these things for delays. We deliberately delay. And I'll show y'all one of the big circuits that we use this for. When we time with a digital signal, and this is on the video, by the way. When we time on a digital signal, what are we going to time on? Are we going to time on a logic? Are we going to time on a level? Or are we going to time on something that I can make sure? So this level right here is going to be impossible for me to time on that level because it's high for a certain amount of time, right? You understand? It'd be impossible for me to time on this low because it's going to be low for a certain amount of time. So what do we want to time on? Somehow we want to come up with a way that we can time on these edges because the edges only occur once a cycle. So that means if I time on the negative going edge, how many negative going edges do we have in a cycle? Well, only got one. How many positive going edges do we have in a cycle? We've only got one. So if I wanted to time something on a 100 megahertz clock, I'm not going to time it on a high. I'm not going to time it on a low. I'm either going to time it on a rising edge or a falling edge. So we got to come up with some circuit that allows us to find the falling edge. And it's a neat little circuit, and we'll show y'all that too. It's called an edge detector. And later on, yeah, it's called an edge detector, and it's not a hard circuit. It seems to prove that De Morgan's theorem is false, or gates are false, but it's going to work out. So this is what we're talking about, and of course, if I can't handle this, so if I'm trying to deal with a 2 megahertz clock, what would be the period of a 2 megahertz clock? So it's going to be 1 over 2 million. And this is time. This would be the period. I think I got too many zeros up there, guys. I had 20 million. So what would be the period? Huh? So how do we calculate period? Period is 1 over time, right? So I take 2 times 10 to the 6, and I'm going to come up here and take the reciprocal of that, right? And that would be 500 nanoseconds. Thank you. So would this circuit work? Well, yeah, it would work because we calculated the propagation delay at what? At 30. That makes sense? Yes or no? Huh? So that means, but it's going to be shifted a little bit because we're going to lose 30 nanoseconds. It's going to be shifted, but we could still get it through there. So what happens if I come up here and start adding more chips, we might get to a point where more gates, we might get to a point where the propagation delay for this series of gates is too large, right? You understand? And then what we might need to do is we might need to go to another family. Power dissipation. First of all, let's look at, I'm going to go back here and tell you something else. Now, what would happen, what would happen I'm going to put 3 gates down here, and I'm going to connect them together, right? Is this good or bad? Well, this is bad. Okay. So we'll use standard series. So these guys here, they can source 400 microamps, and they can sink what? 16 milliamps. Okay. So if this right here is a high, and this right here is a high, let's say, and this is a high, so the output would try to go what? It would go low. But let's say I put a low into this one and a low into this one, the output would try to go what? Can it do that? Huh? Yeah, well, let's just look at this. So this guy here is high. These two right here is low. This would try to drive the output low. These two right here would drive the output high. Could it do that? Yes or no? So you're saying I can put plus 5 volts and ground on the same wire at the same time? Well, that's what we're trying to do, right? So the top one is trying to output a low. It's trying to connect the output to ground. The other two is trying to pull the output up to 5 volts, right? You understand? Now, who's going to win this battle? Well, we don't know. But we got a big problem because when I come over here and start looking at these data sheets, I'm going to look at this guy right here. Can y'all see this right here? iOS. So when we output a standard low, okay. So normally when we output a high, I out high, this guy here can output out high. This guy right here can output 400 microamps. But I'm looking at this dang ISO right here. What is it called? Short circuit output, and that's what we're doing. We're shorting the output of this thing. And how much current could this guy put out? What does it say? It says 100 milliamps. And not only do I have one trying to put out this to ground, I've got 2 trying to put it out in ground. So it means, and they're in parallel. So that means this is 200 milliamps. Now, can this little old guy here sink? What's the maximum it can sink? Well, guy, the maximum it can sink, I out low. The maximum it can sink is what? 8 milliamps. We're trying to make it sink 200 milliamps. Who's going to win the war? The two that's trying to output a high. And it could literally burn up the little sinking transistor on that one guy that's trying to output a what? A low. Y'all understand that? But this would be beautiful if it worked without messing up the gate. Because what I've got right here is I've got any high will give me a low. Any high would give me a low. If this worked, right? Because normally we would think the low would win. So that means if I've got this guy right here is connecting this to ground and these two are highs, then normally we would think that it would pull these two lows. So that means any high would give me a low, which would be an OR gate. You'll follow this so far. But we can't do that. Why can't we do that? Because we'll burn up the other gate. Because these guys are trying to output a true high. This guy right here is trying to output a true low. These guys right here, when we short the output out, what this guy right here is trying to do, that's going to give me 100 milliamps right there. That's going to give me 100 milliamps right there. This guy says, hey, I can only sink what? No, I'm sorry. I can only sink 8. We got big problems. But what would be nice is that I can make any size OR gate only if we could do something about not the low, only if we could do something about the high. Don't understand that? Yes or no? So what they did is they came out with a type of gate called an open collector output. So what do we mean by that? Well, what we mean by that is we come up here and do away with that resistor, that transistor right there. Now the gate can't output a high, but it can output a what? Low. So we can sink, but we can't source. Oops. So what does that mean? So what I've got, so let's look at some data sheets. And what we're going to do is we're going to look at, I think it's 7405. I've lost Blackboard. All I got is data sheets open now. See if it's going to make me log back in. No. What, Joy? 7407 is probably just as good. $74.05 is an inverter. We can look it up. 7407 is a buffer, I think. But what does it say? It says what? Hex buffer driver with what? Open collector high voltage output. So this guy's really neat. Let me get a 7405. We deal with a 7406, right? And we know that's an inverter. So if you're on a data sheet, if Jamico sells it, then if I can get there. And we just come up here and type in 74 LS05, and then we'll search for it. And then, so this is a hex inverter. And we'll go and get the I don't see the, oh, there it is, data sheet. So this is 74 LS05. It's a hex inverter, but it's got what? Open collector output, which means it can't source, but it can do what? Sink. Laid out exactly like a 7404. exactly the same way, the exact same pin out, the exact same truth table. Here they're putting highs and lows, but this thing here can't output a high. So what are we going to do? Well, what we do is we come over here, and I'm going to use a 7405. So that means I have no problem connecting the outputs together. 2, 3, 4, 5, 6. So I got 6 of these in there. So what I can do is I can hook the outputs together. And of course, now if I put a high in right here, it would turn on the sinking transistor and this would go low. Well, what if I come down here and put low on all these? It's not going to hurt anything because these guys right here cannot output a high. That makes sense? But the problem is what would I get if I come over and put that? What would I get? No, I get a nothing. Because these guys can't provide a high. All they can do is provide a low. So how can I alleviate this, guys? And not worry about burning stuff up, not worrying about this short circuit output. We'll come up here and take a little device and put it right here called a what? Resistor. Yeah, pull-up resistor. Normally it's 1K. And then there we go. Now when this guy here, all these goes low, then none of them's going to pull this down, and now the resistor, it would cause this to go high. Right? You understand? But if one of these went high, it don't make any difference. One of them went high, then the output would go low. This would be ground. This would be a 1K. If this is plus 5 volts, then it's having to sink 5 milliamps. If this one right here goes high, this right here will go low. This guy here is already low. It's still going to sink 5 milliamps. Y'all understand what we're saying? Now, what's nice about this, any high will give me a low. So we refer to this, and this is kind of misnomered, by the way, because normally what we do is we put an inverter right here, and then what we end up with is we end up with an OR gate that I control the number of inputs. So this method right here, by the way, is called wired OR. They call it a wired OR gate. And the only way we can do that is if all these gates have to have what type of output? Normally an open collector will give us more drive. So if you ever look at a digital schematic and you see a pull-up resistor on the output of a gate, what do you know about that guy? It's what? It's open collector. So we can use it, the 7407. What did it say about the 7407? What did it say? High voltage output. So instead of running the output on 5 volts, we can put that pull-up resistor. Let's see how much voltage we can get out of the output on there. By the way, this is Schmitt trigger. We'll talk about this later on. See the symbol on the transistors are a little different, and they go through the totem pole, but that's not the output. Here's the output right here, and it's open collector. Open collector means it's not connected to anything. So this guy right here can go up to what? The output voltage can go up to what? 30 volts. So what that means is I can come over here and let's say I want to run a 12-volt light bulb. Well, I couldn't run a 12-volt light bulb with a standard gate, but I could come over here and put this, right? You understand? I could put my light bulb right here, and up here I could hook this up to 12 volts. Over here, we're controlling this with standard TTL logic. This guy right here is powered up on plus 5 volts in common. But the output is not determined by what you power the chip on. It's what's required by what that transistor right there can block, right? You understand? So a 7407 can actually go up to what? 30 volts. What was you going to say, Barry? Huh? Okay. Yeah, so this would be acting like the resistor, but on a 7407, it's not determined on what you're powered up on your chip. It's what you put across that output transistor, right? Y'all understand what we're saying? And a 7407 can go up to 30 volts. A 7405 is still 5 volts, so you couldn't. It's not a high voltage driver, but we probably let's see how much current it can sink. No, it can't sink more than a regular one. It can only sink what? 8 milliamps, which is about standard for a 74LS series gate. Let's see what else I got in this chapter. So open collector, wired outputs, y'all okay? Let me explain the wired AND situation. So you can hear it be called wired AND, or they call it wired OR. So here we got all the outputs connected together. Okay. So if I put, now this is an inverter, so if I'm going to come up here and put a, if I put a high right here, and then it don't make any difference what the rest of them are, right? What would we get right here? Get a low. Now this would try to give me a high, but it can't give me a high. Why? Because it don't have a sourcing transistor. This guy's going to try to give me a high, but it can't give me a high because it don't have a sourcing transistor, right? You understand? This guy right here is going to give me a low, but we've already got a low. It just now we'll have two paths for the 5 milliamps to go through. This guy right here is going to try to give me a high, okay? But it's going to be a low, and this guy right here is going to give me a low. So all these will be low, right? You understand? So what do I have to get down this line right here before I can get a high right there? So what would I have to get out here before this pull-up resistor right here wouldn't drop any voltage? Come on, guys. I mean, the only thing I can do is for all these right here to be what? Yeah, so if I can get all these high, then this right here would go high. So this guy, this right here, this circuit right here is acting like a Watt gate. Took all highs, like an AND gate, huh? I'm listening, Barry. Yeah, we're not looking at, I understand what you're saying. Let me get rid of all this stuff over here. I don't want to confuse y'all, even though I know I do sometimes. Some people call this wired OR, and they call it wired OR if you use this whole circuit right here. Some people call this a wired AND. So a wired AND would be this circuit right here, where I've got these inputs by itself. Okay, and then I'm gonna come over and connect them together, and I'm gonna get an output. And I'm trying to get a high right there. To get a high right there, what do I need? Right over here. So if this is a low, and I've got that pull-up resistor, then I don't care what I'm trying to get out of here. They're all going to be lows, right? You'll understand that. So what do I need to get a high right there? Well, the only way I can ever get a high right there is if all these inputs are what? If all these inputs right here are high. Now, what logic is that? All highs to get a high. No, this is AND. So this circuit has two names. They'll refer to this circuit either as a wired or they'll call it a what? A wired AND. Now, the only way we can do this is that the gates we use to bring in this AND right here all have to have what? They all have to have what? Open collector outputs. And what can an open collector output do? It can only do one thing. What can it do? Starts with F. F. It can sync, but it can't source. Open collectors can't source. So that means, what do we always have to do if we're using open collector gates? We got to have a what? Pull up somewhere. So what happens is the pull up provides the high and the gate provides the low. Y'all understand that? We got one more output that I don't know when the book is going to get into it. We got another output called tri-state. But what it gives us, the open collector gates gives us the ability to do what? Well, one thing, it gives us the ability to the 7407 gives us the ability to also change the logic level. So instead of using TTL levels, now we can go to a different level with the 7407. Also, it gives us the ability to tie the outputs of gates together without damage. If they've got totem pole outputs and you connect them together, they might work for a while, but sooner or later that little sinking transistor is going to give up the ghost, right? You understand why? Because it can't handle those short circuit outputs. So we can get quite a bit of current out of a gate, but it no longer does the right. It no longer gives us 2.4 volts. So as soon as you get above the rated output, the maximum output current, then the output's going to start dropping down. Eventually, you can load it and you can short out the output of a standard TTL gate. But you don't need to do it very long, right? You understand? Because it's going to try to be sourcing 600. This other guy was 100 milliamps through that little 130 ohm resistor, and if you do it very long, you're going to mess it up. But it's good enough to troubleshoot. So yeah, we can jump out. We can ground the output of a logic gate without hurting it, so we can see what effect it has down the line. In fact, we got a thing called a logic probe that basically that's what it does. A pulsar probe. So this is open collector. Everybody okay? So we basically do away with the sourcing transistor. And so now the gate can only do what? I know I said it started with an S. Sourcing starts with an S too, but this guy, it can only do what? Sync. It can only provide the ground. Something else has to supply the voltage. This allows us to do what we call wire GANing or wire ORing, which is pretty neat. But the only way we can legally connect the outputs of gates together is if they're what? If they're open collector. Y'all understand that? Well, that sounds like a good test question, doesn't it? It just looks like a question on the test. So 7433 is an open collector. And this is why we got so many dang gates, because not only did we have all the families, right? Y'all understand that? But we also got different outputs. Right now we know we can have a totem pole output or we can have an open collector output. There's one more output arrangement we got. It's called a three-state output, which means it can output a high, it can output a low, and it can output a nothing if we wanted to. And those are the three gates. So that's why we got so many different gates, is because not only do we have different families, but we got different capabilities on the output, right? 748 series, what they did on the 748 series is they halved all the resistors in the gate, which means the gate would run twice as fast as a 7400 series, but it had half the propagation delay, but what? Double the power consumption. So the 74.8 series was the first true high-powered or high-current, high-powered, high-speed chip, but it came as a big sacrifice. So then they came out with what they call a Schottky diode, which what was happening was so we can operate this transistor in 3 different regions. What 2 regions do we use in digital? So what 2 regions do we got? Cutoff, saturation, and active. What 2 regions do we use in digital? Y'all don't know, guys? So what 2 regions? Saturation and cutoff. When we saturate it, it acts like a closed switch. When we cut it off, it acts like an open switch. So that's what we're doing in TTL. We're either turning these transistors what? On, or we're turning them off. Now, when you take solid state, we'll spend more time in the active region because that's when we can amplify stuff, right? So when you got a stereo out there, it's not operating we're not cutting on and off, we're operating in the active region. Your outputs are. We can do a lot of digital stuff on the front end, but by the time it hits those speakers out there, we got to be in the active region. Now the problem is to make this thing work, and what type of transistor is this? Sometimes I think I'm the only one listening to my lectures. So what type of transistor is this? Huh? No, you're talking about the resistor. I'm talking about the transistor. So we got 2 transistors. We got an NPN. Y'all remember way back at the first of the term? And we got a what? PNP. So what type is this? This is an NPN because it's not pointing in, right? And we can tell by looking at the arrow. So this is an NPN. So what do we need to turn it on? Well, what I have to do is I have to make the gate, the base, I have to make it positive in respect to the emitter, 0.7 of a volt, and then I'm supposed to make the collector much more positive than the base. So this guy right here is what we say reverse bias. This guy right here is forward bias. Now the problem is when I turn this thing on and saturate it, then what happens is this resistor drops 5 volts. This right here goes to 0, and now we're forward biasing this junction right here. So what happens is the base to collector junction builds up a charge, a capacitive charge. So what happens when I bring this back to 0, this transistor has to cut off. Well, it takes a little time to cut off because it was saturation. It takes a little time to get this thing out of saturation. So what they said is that they said, well, we can move it towards saturation, but if there was some way I can keep it out of full saturation, then I could cut it off a lot faster. So they came up with a special diode they call a Schottky diode, spelled just like it sounds. And what they would do is they would put it in there in this direction right here. And the Schottky diode has a symbol that looks like this. So what happens when this tried to go to 0 and this right here tried to stay positive, it would forward bias this diode and would not let the transistor go into full saturation. You'd always have the diode drop of this, which was around 0.3 of a volt. So now the transistor would not go into full saturation which means we could switch it off faster. Now follow this. Now these became so popular, the diode right here became so popular, eventually they just integrated it into the transistor, and then they changed the transistor symbol to look like this. So when you look at these logic gates and you see this transistor symbol, it means that is a Schottky barrier diode, and these guys don't fully saturate and they will operate extremely fast. Rule of thumb for Schottky, for S-series integrated circuits, rule of thumb is around 3 nanoseconds per gate. These guys will scream. We're talking nanoseconds, guys. Now, what they realized is they came out with a 74L series, and what they did on the L series is they doubled the size of the resistors. So if they doubled the size of the resistors, then the gate would pull half the power, but would run at half the speed. Well, when they came out with the Schottky barrier diode, they came out with 2 series. They came out with the 74S series, and then they came out with the 74LS series, which is a low-powered Schottky. So they doubled the resistors, but they used Schottky diodes. So what we got was we got basically the same propagation delay as a standard series gate. So what happened to the standard series gate at half the power? It's gone. You can't hardly find standard series gates anymore because of the what? Before the LS series. So we got basically the same performance. It was a little better. Rule of thumb propagation delay for standard series is about 10 nanoseconds. For Schottky, it's like 9. So you didn't get that much of a speed boost, but you did it at a lower power consumption. Then Fairchild came out with some high-speed chips, and they started theirs with L. So these were all made by Fairchild, which is a semiconductor manufacturer. If y'all have never heard of Fairchild. They called it the F series. In fact, some of them, then we had advanced low-powered Schottky. So these guys were faster, right? You understand. I don't know the propagation delay on that. We'd have to look at the ALS series. We got some ALS series, and then Fairchild put one called the FAST. So 74 FAST 04. Don't they even sound cool? And what does it stand for? Fairchild Advanced Schottky Technology. So this was their series of gates. Then we came out with what we call the complementary metal oxide semiconductor family. And this is probably where we're going to lay off and let y'all take a break. Take a break. Polar transistors is it takes a current to control a current. And then, of course, when we take them into full saturation, we have problems getting them out, right? You understand that? Plus, they consume quite a bit of power. So what they were doing is they were looking for an extremely low current capability, low power circuitry, but that when we wasn't concerned with speed. So the next transistors that came out was ones that we refer to as metal oxide semiconductors. Have you ever heard of MOS? And we call these MOS. We got several categories that you'll learn about in solid state. We have what they call EMOS, and we have JFETs, we have MOS, we have EMOS and DMOSs, but here we just use one type in digital, so it's no big deal. Now, what was so cool about the MOS is they can serve 2 functions. They can serve as the resistor, or they can serve as the switch. So right off the bat, what would happen is I could come over here and literally have an inverter, and this is simple, and put what we call a PMOS up here, put an arrow in, and then down below it I would put an NMOS, So this is a PMOS pointing out, an NMOS coming in, connect these outputs together, and that was an inverter. 2 transistors to get the same thing that took 5 transistors in a 7400 gate. So all of a sudden now we had the ability to put more integrated circuit, but the way these things work, so when this guy right here turns on, this guy here acts like the resistor, right? You understand? And of course, when this guy turns on, this acts, and this is off, this acts like a resistor. So we have a pull down and pull down resistor. We don't have to do anything about that, and they work out real well. But the problem is they consume very little power, but they're very slow. So a lot of your battery operated equipment still runs off of CMOS because it consumes so little power, but we're not concerned with a lot of speed, like the remote on your TV. I mean, how fast does it have to be? It don't have to be fast at all, but it runs off little old tiny batteries, right? Most remotes run off like 2 AA batteries, and that's only 3 volts if you hook them in series, right? Which they usually do. Another thing that was nice about CMOS is the range of voltages we could operate this thing on. These guys here could operate on like any voltage from around 3 volts up to 17 volts. TTL had to be 5 volts plus or minus 5%. CMOS, since these are voltage controlled devices, they're not current. So what a MOS does is a bipolar transistor uses a current to control a current. Now, what MOS does is it uses a voltage to control a current. And there's no current flow into this lead right here. So your bipolar transistors, you always conduct a current. Over here, what we do is we put a voltage on there. And there's no path. There's no current flow between what's driving it and what's being driven. So we had 2 logic families for years. We had TTL, and we had CMOS. Complementary, because this is what we call an N channel. And this right here, this is what we call a P channel. And this right here was what we call an N channel. So they were the opposite of, and this is where the complementary came from. If you're been around computers for a while, you understand that these computers have to be configured, and we have a section they call the CMOS. The CMOS. You ever heard of that term for CMOS setup? Well, you can still get into them if you know how to and change the boot sequence and stuff. Well, all it is a little tiny piece of CMOS memory that we keep. There's a battery inside there that keeps that power on there when you turn your computer off. And that battery's like will hold it for about 10 years because that CMOS almost uses no current at all, right? Ever heard of CMOS memory? So these are called CMOS, uses what's called metal oxide semiconductor field effect transistors. And we have 2 types. We have PMOS and we have NMOS. PMOS takes a negative to turn it on. Let's see, yeah. NMOS takes a positive to turn it on, just opposite. So that's the way we do it. 0 volts would be considered a negative compared to the other one, and then of course positive would be that. What this gave us the ability, so microprocessors are made of this stuff because the transistors are a lot smaller. We don't have to put any resistors, right? You understand? Because these things can, when they're off, they can substitute as a resistor. So your microprocessors are made out of MOS. The problem we have with MOS is that the coating, the insulator that's between the lead that we call the gate, we call it the gate, is an extremely thin insulator between that. And we have a tendency to build up charges. And if you touch that thing and you pop it or discharge through that CMOS, you could rupture the insulator that's between the gate and the other two leads. So MOS circuits are susceptible to damage with static electricity. So you got to be real careful when you're handling the memory of your computer or your processor or anything inside that computer, because there's a lot of MOS in there. And you could damage it just by doing what? Just by handling it. So this is why when you go out and buy like a new motherboard, if you're into building computers, it's going to be in an anti-static bag. All your memory is going to be in special packages. And then we have special considerations. This right here is called a static armband. That's all it is right there. And all you need to do is just, with this guys are less than $10, you just put them on your arm. And then, well, you have a static mat that you set stuff on. You clip this onto your mat, and everybody gets at the same potential, and you can't hurt it. It's called a static wristband. You see guys that are really, really susceptible to static discharge. They'll have a static thing around their ankle with their wearing tennis shoes, and it's just a pad down there that discharges them. It's just like me. You'll see this. You know what that is? Can you see it? What is this? It's a grounding wire. That's all it is. It keeps my wheelchair from building up static. I mean, this chair used to be awful because it's got plastic runners on it, and I'd be whipping down in the wintertime where all the moisture's out of the air anyway, and I'd be whipping out down there, and I'd lean over to get a drink of water, and I'd arc through the water on my lips. I couldn't touch anything. But ever since I did this, now I can't. Now the chair can't build up a what? Can't build up a charge. I can't get a charge relative to the store. So y'all hear it dragging every once in a while. But that's my static discharge. So when you start playing around with MOS, guys, you need to make sure you guard against static discharge, right? You understand? If you got a bag that's got it in there, you need to place the bag on whatever you're going to be working on. If you don't have a static wristband, then you need to constantly touch and make sure you're discharged against whatever you're working on. These guys right here are not very expensive. If you're going to work on computers, I highly recommend that you get one. You can get them through Zamaco, by the way. I think they're about $6 a piece. And you can get the mats too. The mats are really good because what you can do is you take the mat and you clip it on to what you're working on. Then you clip yourself onto the mat. And then when you buy this stuff, you put it on the mat. And it don't discharge rapidly. These bands are designed, they have a resistance in it. Because if it didn't have a resistance in it, you would discharge when you put on the band, right? But it bleeds you off is what it does. It bleeds you off slowly. We can go over there and pop the CPU cover, the cover off the controller on the big Fanuc robot, and what do they have inside that thing? They got a static band that came with the controller, the static wristband. So higher package density, which lowers the cost of millions of memory cells per chip. This is when we start talking about the memory. So the memory in your computer is MOS. And just about every computer gives you the ability, except for your laptop, I mean your tablets, to upgrade the memory in your computer. But when you start popping that stuff out and you just handle it with your hands, there's a high probability that you could damage it. And a lot of times you'll damage it, but it works for a little while. This is like when you run over a nail with your tire. Usually it don't go flat instantly. It takes a little while for your tire to go out. So this is the basic difference right here, which is not really important for us to know. But the leads on a FET, a field effect, metal oxide field effect transistor, called the gates and the drains and the source. And the gate is kind of like the base. And then the drain is kind of like the collector, and the source is kind of like the emitter. But these guys right here, the gate is insulated from, it conducts no current, which is pretty neat. So TTL, the advantage of TTL over CMOS is that it's faster, but the biggest disadvantage is it consumes a lot more power. And if I'm not concerned with speed, then odds are we're going to use MOS. Now, they came out with a 4000 series, and it was totally not compatible with TTL. They did that on purpose so people wouldn't screw up and put these things together. because a CMOS gate would not run a TTL gate at all. It just couldn't put out the current required to do that. But then they started coming out with, so 4000 series, those are getting harder to find because of these guys right here. So used to in the old days, 4000 series was CMOS, 7400 series was TTL, and they were not compatible. You couldn't mix them in the same circuit without going through what they call a level converter chip. And then they came out with the 74HC, and that blew everything out of the water, because what do you think the C stands for? CMOS. With a 7400 series. Man, this blew me bad. Because they're PIN compatible, but they will not drive TTL. So now what could you do? You could screw around and mix them up, and you saw a 7400, and you said, well, the only difference between these center letters is the speed and the power, and you say the pin out's the same. Well, the pin out is the same, but a 74C would not drive a 74 series, a TTL series gate. So then they came out with the HCT, the HC and the HCT. The HC will drive them, but not many, and then the HCT basically will drive TTL gates without any problem. And y'all saw those too, right? Y'all dealt with an HC and HCT, one of y'all's first labs. These are CMOS. The HCs and the HCTs are pin compatible with CMOS. The HCTs will work in a TTL circuit. And then these guys we're not going to talk about because I've never seen them. These are becoming very popular in computers because computers, the lower the voltage, the faster they can switch. I don't know if y'all can understand that or not. So usually when we get inside the microprocessor, so used to in computers, we had 3 power supplies. We had actually we started off with 4. We had a plus 12, a minus 12, a plus 5, and a minus 5. But what they've done now, if you're dealing with the motherboards, is everything's dropping down to these voltages right here. 3.3, your processor's using 3.3. Now the microprocessor usually has about 2 or 3 voltages that it uses. It uses a 5 volts to drive the buses. It uses 3.3 to drive memory, and it uses lower voltages to run inside. So, but this is, let's go ahead, emitter coupler, extremely fast. They're talking about comparing. This is what we want to look at right here. This just gets a basic feel. So where's this figure 9.3 in the textbook? So these are rule of thumbs or generality, and what they're doing over here is they're saying, okay, if we looked at the data sheet, we'd see most 7400s have a propagation delay of about 10 nanoseconds per gate, and it consumes about 10 milliwatts per gate. And then they came up with what they call a speed power product. Can you see how they came up with that? And they just took the propagation delay and multiplied it by the power distribution per gate, and then they came up with the speed. So the better this is, that means the overall power versus speed would be better, the lower the number, right? Then they came out with the S series. What's the propagation delay? Typical propagation gate for a 74 S series? Right here. 3, but it uses 20 milliwatts per gate because it's faster, but it consumes more power. So it's a little better than this one because it's got a speed power product of 60. The LS series, which is what we're using a lot of, right? You understand. Most of our gates are LS series or LS family. So these guys have a propagation delay around what? 9. And then power dissipation around what? 2. So guess what disappeared? These guys are gone. These guys you can't hardly find anymore. The LS series is the predominant used version of gates now. And y'all can see that. Everything we got is probably LS. It's got a speed power product of 18. Then we got the ALS, which is the faster version of the AS. And we ran into a lot of these inside computers. So these guys here have a propagation delay of about 4 nanoseconds. So that's why we don't see many of these anymore because of the ALS series, right? You understand that. It's the propagation delay of 1 milliwatt, power distribution of 1 milliwatt per gate. Look at that. 4. Then the 400 series, look at this. Propagation delay is around what? Yeah. And then they don't give us milliwatts per gate. They give us 1 milliwatt, but at 1 megahertz because it varies with speed. So look at that. So this is, I would use these guys. Used to we use these guys in battery powered equipment, and that we wasn't concerned with speed, right? And then these other guys you can see that we're not going to talk about. And then ECL is the fastest, and but it consumes what? Most power. That's some high speed, high power circuitry. So this just gives us a little feel of the comparison between these different families. Now this could be a 7400, this could be a 74 S800, right? You understand? Now we have a fairly good idea of the difference between these family designators. And then this is a nice graph that shows that, but we're not going to look at it. So that's it for chapter 9, everything we're going to talk about. So y'all got any questions, anything you want to go back and look at? And we got a little look at the data sheet, right? You understand. We understand, of course, the big things are propagation delays and current draws, the voltage levels and the current, or the required current on those supplies. Okay, guys, let's go to lab. If y'all don't have any questions, y'all got any questions, ask them now.